I'm your instructor. We have a couple examples to start off with. These were on Smart Site. We'll just kind of tackle them one at a time. It's a pretty, at least they follow what we've been doing here. This first one is a little bit of a tough one. This is about isotopes. We want to find the molar mass of mercury. Now, if I wanted to be somewhat pathetic, how could I possibly know what the answer would be? I'd probably look at the periodic table. I better get a number around 200.59. Okay? So that, my answer should be somewhere around there. But on exam, I need to show work. So that's what I'm going to do right now. In order to find the molar mass of something, that will equal the sum of the percent abundance, which I'm going to change to a fraction. So basically I'm dividing this column by 100, change it to a fraction. It's really a fractional abundance times the mass. And the mass, I mean the isotopic mass, so the mass of the specific isotope, which is here the second column. So really I'm multiplying the second column by the third column, but really the third column I'm changing to a fraction. So for example, the second one would be 0.1002. Not 10.02. So what I'm going to do is make a third column now of this here. I'm going to make it just here on the right hand side. And I'm going to just multiply the second column times the third column. And see what numbers I get. Now I'm going to keep a lot of digits in the beginning. And later I'm going to figure out what's what. So the second one is 19.83, 6273. The third row, when you multiply those, you get 33.50, 6262. The fourth row is 46.25. And I'll zoom in so it's just a little bit easier to see here. Okay, 46.25, 2668. The next row, when you multiply those, is 26.56. Again, I'm just multiplying the second row times the third row, second column times the third column. A third column would be a fraction. 26.568274. Next one would be 13.972.185. And the last one is, this one is 60.187239. So I flipped the bottom two accidentally. Okay, once I multiply those all out, okay, for every row, now I'm just going to add them together. So the sum, this is the sum part, I sum them together, let's see what I get. I'm going to get 200.60901. And that's really my answer. The only part I haven't, which is pretty much exactly what you see there on the periodic table. The only issue is I need to find the correct number of significant figures. So let's do that. So you need to look at each one. For example, this, when I multiply these two, how many sig figs will I have? Yeah, this has 7, but this has 3. So I'm going to underline these 3 right there. The next one, though, will have 4 sig figs when I multiply these two. So 1, 2, 3, 4. The next one will have 4. The next one will have 4. Next one is 4. And then the next one, we're back down to 3 again. 3 for that one, and then 3 this one. Okay. So I just underlined what are actually sig figs, okay, or my significant figures that I can trust. Now that I'm going to add, so remember all this is adding. What I need to do is line up the decimals. This is my method. I line up the decimals and see where my last significant digit ends. So here, 3 places after the decimal, tens, hundreds, thousands place. But that's limited by the next several, which are in the hundreds place. So here, this would tell us this would be the last digit. But then when I get to the last two, they're limited by the tenths place. So really, my significant figures ends right here at the 6. So everything I'm underlining, 200.6, would actually be my significant figures. Again, limited by the last two digits here in the column, the 60.1 and the 13.9, because they end in the tenths with significant figures. This must end in the tenths. I can't go out to the hundredths or the thousandth position. So my final answer would be rounding, just rounds to 6, 200.6 would be my final answer. Any questions on this problem? Follows the same procedure as other ICO problems that just had a lot more math. Yeah? How would we do this? This question is on an exam. You can do it as I did if you show that these two are being multiplied together, or you can write it out step by step. Either way would be fine. We need to see some work, yeah, on an exam, but this would be fine as long as you show something like this where it shows, oh, I'm multiplying these two columns. Depends how the question is given on the exam. Okay. Cool, that's that one. Let's go to the next one, which I believe was this one here. What's that? This is a chapter 3 problem here, just to make sure we understand the terms. Let me make sure we got these terms down. I think the easiest one to start with would be the molecular formula. So let's start there. You don't have to start there, but I think it'll be the easiest. Molecular formula is a list of each atom and the number of atoms included. So it's a pure list. So carbon, there's 1, 2, 3, 4, 5, 6. C6. Hydrogen, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then oxygen, 1, 2, 3, 4, 5, 6. There we go. That's my molecular formula. It's a list of each atom and the number of atoms that exist. The next easiest for us, this out of the way, the next easiest will probably be the empirical formula. That's merely where we divide through the molecular formula, really to kind of give the least common factor. So you divide through by 6, CH2O. So there's 1 carbon, 1 oxygen, and 2 hydrogens. I'm dividing through by 6. Then I have the chemical formula. And by the way, you should have seen last time, the molecular and the empirical formula are interesting and helpful to us because those we can calculate. So you already should have done a couple examples with Josh last time. Because we're doing combustion analysis this time, you're going to see a couple more examples. Okay, the chemical formula can, actually a number of answers could be viable. Chemical formula basically shows some chemistry of it or how the connectivity works. So there's a number of ways you could probably do it. I'll just show you one example way. So let's just start at the top. There's a CHO group. CHO at the top. There we go. CHO. And then notice the next 4 are a carbon with 1 hydrogen and 1 OH. That's the next 4. So we've got a CHOH for the next 4. Okay. And then we've got the CH2OH. Now this would not be the only necessary answer, but I'm showing how things are bonded a little bit, and one comes after the next. Though I'm not drawing it in the original form, which we would call the structural formula. So the original one that is printed in the upper right, that's called the structural formula. I take away some of the structure, but I'm still showing a little bit. So that would be an example of the chemical formula. Okay, any questions on this? We have one more. Question? Why is carbon always in the front? Just by convention. We usually put carbon first. Like, not always. It's just a set of conventions you get used to as you get into chemistry. Had you not done that, I wouldn't mark you off, except I just said it. So now you have to. But usually you'll go carbons, then hydrogens, then oxygens. Typically. It's pretty standard convention. Okay. Let's do the last example I had up here, and I believe it was this one, the styrene, which is from the root from polystyrene. This is where we get polystyrene or our plastics. And this is a molecular formula problem. And before we do this one, let me just review a little bit here. So I'm going to remove this for a moment. I'll put it back, don't worry. You'll see this in your reader. This is on page 14, something like this. There's 3 types of composition problems you're going to see in chapter 3. One is percent mass, and the percent mass, that's just fine with percent mass. You should have done examples of this with Josh. It's where you take the system mass, or the mass of what you're interested in, divided by the total mass, times 100. So depending on what you're given, it will change a little bit how you calculate it. There's also a similar problem called the empirical formula. The empirical formula, the key unit is moles. So if you didn't know that the key unit for empirical formula problem is a mole. Then you divide by the smallest and round to the nearest whole number. So using the law of multiple proportions. And then the molecular formula is what we're just about to do. And that's where you take the molar mass of the empirical formula, or molecular, and divide it by the empirical. And here's how this is typically going to work. The molecular formula is going to be a given number in the problem. So the given number will go in the numerator. It'll also be the largest number will go in the numerator. Okay? Then in the denominator, you will have access to the empirical formula, and you're going to calculate its molar mass, and you will put it in the denominator. That will be a smaller number. Okay? You're going to divide those two. You'll get a whole number. If it's not a whole number, you have messed up somehow. So anyways, we're about to do one of these on the right. Okay, let's try this. And that basically summarized a big chunk of the types of problems we see in this chapter, the composition problems. Okay, here we go. So notice, I am given this one right here. That's the molecular formula molar mass. Okay, that's the actual molar mass. That's my given. And then I also have access to the empirical formula, CH. So what I'm going to do is find the molar mass of this. Okay? So I'm going to find the molar mass. If I don't have a periodic table, just look at your tie. Grab myself. Don't worry, I don't wear this in public. Okay, CH, that'd be 12.01 plus 1.008, or just about 13.02. And then you take the larger number, the empirical formula number, 104, divided by 13.02, the empirical formula number, and I got 7.989, which is really normal. You better get a number super close to a whole number, if not exactly a whole number. This is 8. Okay, so you can round here. You don't have to worry about sig figs when you're doing an empirical formula or a molecular formula problem. Don't worry about sig figs there. And so we got 8. That means we take CH, and there's one of each of those atoms, multiply the subscripts by 8. So the final answer is C8H8. Okay. So that's my molecular formula. And you wouldn't have known this part, but you probably have figured this out after we get to chapter 9. But this is styrene. This is C8H8. That double bond there allows for it to polymerize and make polystyrene. So, but you wouldn't have known that. I'm just drawing it for fun. This is what you would have wanted to get to right now. Okay. Any questions on this one? Often on exams, we'll pair up an empirical formula, a molecular formula problem, and a percent mass to make it one monster problem. Okay, so that's pretty common. And you'll see some example. You saw Josh do some you'll see we're about to get to a couple more. Okay, we cool with that? Alright, alright. Now, this, for those of you who are anal and like making lists and checking them off, and even checking off stuff we've already done, you're going to love this part of the class. You always see me make a check mark here. Check, we're doing chapter 3. We should probably finish it, okay? We got a little time for exam 1. By the way, here's my office hours. If you didn't know them, they'll be tomorrow morning. If you want to join me, you can come at any time. And if you come, just sit there and listen to other people mooch off their questions, okay? So you don't have to have a question if you don't want to. And then we'll probably end a little bit early. Head to my office if anybody has like one-on-one questions. Last maybe 20, 30 minutes. I'll take like individual questions. But most of it will be in group time. Okay, so you did chapter 2. From chapter 2 with Josh last time. Well, even with me, we did the little historical bit. And then after that, you should know how to calculate protons, neutrons, electrons from any given ion or species. You should be able to find molar mass, know about the periodic table. The chalcogens is what column? What's the top atom in the chalcogen column? What's the atom at the top of the chalcogens? Oxygen. Yeah. What's the atom at the top of the halogens? Fluorine. Okay? Stuff like that. That's all in the reader, page 10. Make sure you can do isotopes and simple mole calculations. That's all chapter 2. And I just brought a funny example here for moles. Here. Just so you can see kind of a visual. Here's a mole of lead. Okay? Kind of get that visual of that volume there. And you can see this from the periodic table. There's a mole of lead. Here's a mole. You can see it's a much different volume of sugar or sucrose. Okay? Much larger. Here's a mole of sodium chloride, which is? Yeah, table salt. Sodium chloride. All these, we can figure out the mass, so the molecular weight is from the periodic table. Okay, you can see the volumes are all different. We've got, here's a mole of dichromate. Chromiums can be a bunch of different colors. Here it's a bright orange. So moles, just because it's a mole doesn't tell you the volume. It just allows you to calculate the mass. Here's a copper. Copper is often blue or green. So that's a mole of a copper sulfate pentahydrate. Here's a mole of water. Now, why is the water blue? Yeah, I put food color. And here, here's a mole of mercury. It's a liquid. Is this light? No, I'm just really strong. This is a mole of mercury. It's pretty heavy. It's very dense. It's not the most dense metal. Osmium is really dense, but it's pretty dense, very heavy, actually. And it's pretty dangerous. Somebody's working, these last few years, a researcher was working with some mercury compound, not this, and she got a couple drops on her glove, on her lab glove. She said, oh, that's not a big deal, just rinse it off. What she didn't know is it had went through the pores of the glove, and she ended up, a couple months later, ended up in a coma and passed away because of mercury poisoning. So mercury is something you need to be really careful with. I also brought about a mole of air. Here, about beach ball size is a mole of air. And it's about, what do you think, does anybody know what the volume approximately is of a mole of air? About 22.7. We're going to see that when we get to the gas chapter. Now I'm going to whack this into you. I don't want anybody to, when they get it, to like slam it into the person in front of you. Okay? Let's try that. See how it goes. Oh, careful, 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 careful. Oh, nice. Okay. Let me be alive. So you guys don't feel jealous anymore. Okay. So molar air is about 22.7 liters per mole. Oh. Okay. Go back. Stop. All right. We'll play volleyball later. We're going to go on to what's called combustion right now. Combustion. Let me write out a combustion reaction right at the bottom of the page we were working on before. Combustion reaction is as follows. You take an organic molecule has carbons and hydrogens. It doesn't matter how many carbons and how many hydrogens, so I'll put X's, make it unknown. Oh, and this in the reader, we're starting on page 16 or 15 really, and in the textbook, this starts on page 84. Okay, and it could have other atoms on here. You add oxygen, and you're going to form CO2 and water. And which, when we get to chapter 4, we'll talk about balancing. But that's a typical combustion reaction. You add oxygen, you get CO2 and water. Now, just as kind of related, but not at the moment, you've heard of haunted house. So, there's this famous case of haunted house in 1921. These couple moved into a new home, and soon after they moved in, they started hearing sounds. So they started to get headaches, they were fatigued, they began to hear bells and footsteps in their house. They started to feel physical sensations and see figures kind of walking around their house. So pretty creepy. So then an investigator went to their house. Oh, and previous people in the house also had similar experiences, so it wasn't just them, okay? A guy, Dr. Wilmer, went there and kind of studied this situation, and ultimately he ended up going down to the basement, and he found out that their furnace was broken, and it was leaking CO, or carbon monoxide. So he had it fixed. And amazingly, after that happened, the ghost went away. And it turns out that that's some of the side effects of CO, or carbon monoxide poisoning. And it's estimated even today about 40,000 people in the U.S. undergo CO poisoning. And how does that happen? It's with the combustion, in their case of the furnace, undergoes this is called really complete combustion. If the combustion's not complete, instead of making CO2, it makes carbon monoxide. So that's why out the back of your car, sometimes if there's not complete combustion, you'll get carbon monoxide out of the exhaust instead of CO2. You should have coming out of it. Now, combustion is helpful in chemistry because we can do something called combustion analysis. It's from your text. If you want to see it, it's on page 84. But just looking at the picture should be fine. What you do is you put a sample in a furnace, and if it's an organic, you add oxygen and it'll combust. And then it gives off water and CO2, which you can put an absorbent to capture that. And then you can measure, really the top part of the picture is most important, you can measure the amount of H2O and CO2 collected, and you can determine the empirical molecular formula of the original compound. Why is this interesting? Well, not just because of that, but also, you could put like a pie in here, which is what they selected to put in here. And this can happen, you can do this too. In fact, you learn in 2B, you look on the back of your cookie package, it has so many calories in your cookies. You know what I'm talking about? You're like, I can't eat that many calories, but it doesn't matter. Those calories are determined by something like this. You can also find the calorie, literally the calories, and that's how they determine that. And Chem 2B, you probably will work on that. Okay. That's a little bit on us. We're going to work on the chemical, molecular and empirical formulas. Now, how do we do that? There's, no, not that color. Let's do this color. Solving empirical. I'll just abbreviate empirical formulas. And formula will abbreviate. Oh, by the way, the cameras here, we're going to record, whenever I can, I'll record the lectures and we'll post them on our YouTube site. So if he was blubbering at one point, I didn't understand what he's saying, you can watch it again later. So hopefully that'll be a good aid for you in class. Okay. The first type, and this in the reader is page kind of 16, 17, is what I call other, and it's what we've done already. The other kind of generalization, in general, how do you solve for empirical formula? First, you find the moles of each element in the compound, and then you divide by the smallest. So that's what you did with Josh last time. Okay? Find the moles, and you divide by the smallest. Done. That's it. But there's a different kind that I'm alluding to now. It's called combustion analysis. This is a different kind. It's still the same kind of solving, but it has some extra steps. So combustion analysis. How does this work? You're going to be given, in this kind of problem, the mass of CO2, because a combustion reaction happened, and the mass of H2O. That's your given, so that's where you start. Where do you go from there? You're going to change that. Remember, the key unit is moles. So you're going to change to moles of CO2, and then moles of H2O. So use the periodic table to do that. Then, from there, and I'll show you how to do this, you're going to change to moles of carbon and moles of hydrogen, the atom itself. Okay? And I'll show you how to do this. And then, you're going to ask yourself a question. Is there oxygen? So is oxygen in the original compound? So there's two possible answers, of course. No. Well, I guess there's three answers. Yes, or not sure. Yes and not sure are going to be the same answer for us. Okay, let's do the no answer first. If you determine there's no oxygen, then you're going to go to your empirical formula, where we'll just have carbon and hydrogen. And it'll be, we don't know the subs, I'm just talking in general now, so I'll just put an X and Y. What I'm going to do, let's go to a different color. How do you get X and Y? The moles of carbon is X. Remember, that's a key unit for empirical formulas, and the moles of hydrogen is Y. So that's where you find X and Y. And then your last step is divided by the smallest. So it has the same ending as the other section. There's always the same ending of divided by the smallest. But if there is oxygen, or if you don't know if there is oxygen, then we gotta keep going down this way here. So if you're not sure, or if there is oxygen, what you're gonna do is change the moles of carbon to mass of carbon. You can change the moles of hydrogen to mass, or little m, hydrogen. And then you're gonna use the following formula. The total mass of the compound I'm interested in is equal to the mass of carbon plus the mass of hydrogen plus the mass of oxygen. So now we're assuming there's oxygen in there. Okay? And what you're going to do, you know the mass of carbon because you just found it right there. You know the mass of hydrogen because you just found it. And the mass total is given in the question. So the only thing you're not sure about is the mass of oxygen. So you solve for the mass of oxygen. Mass of oxygen. And then you convert that to moles of oxygen. Remember, moles is the key unit, but this is the only way to get it for an empirical formula problem. And then, I guess I'll write it up here. Now your formula has carbon, hydrogen, and oxygen. Let's just say CXHYOZ. And you've just found Z. It's this right here. The moles of oxygen is Z. So you have X and Y from way up here, and you've got Z, the subscript there. And what do? You divide by the smallest. So as you can see, there's additional steps. You'll have to remember how to go through these steps. It's following the same concepts that we learned in Chapter 2. There's no difference. The concept is about the law of multiple proportions, which it says that every subscript is a whole number, a small whole number. So it's following that same concept, and you get there via moles. And we're going to try an example of this. I'll put it right here. 5. And there's a lot of examples I have on YouTube. If you want to see some extra ones of these, I'll put those other examples on these post-its. They're also in your reader, but just so you can see them. Another place, put them on these post-its. But they're labeled in your reader. There's combustion analysis A and B, there's combustion analysis, there's crazy amounts of stuff. So, please go see extra examples. Okay, this problem, that in the dorms there was this drug raid, okay? Maybe your roommate, who knows? And then they took the sample and they're like, what do we do? And you say, I was in chemistry class, I'll take the sample, don't worry about it. And then you do this analysis, you find how much CO2 and hydrogen comes out of your combustion analysis chamber, okay? And you know, you're able to find the original molar mass, which is 180. So we want to determine the empirical formula, and ultimately that we're going to find the molecular formula of this evil substance, okay? This white powdery substance, whatever that is. All right, so that's what we're going to do here. Okay. Now, I'm going to follow the procedure that you saw in that flow chart we just did a moment ago. Okay, so that's what I'm going to follow. And we're starting off with, let's see. Let's do CO2. That's how much? 0.1486 grams. Okay? And so what I'm going to do, I'll do this first for CO2. Use the molar mass from the periodic table, 44.01, to convert to moles now of CO2. That's my first step. The next step, you'll see in my little flow chart, is to go to moles of carbon. So how I do that? There's 1 mole of carbon in every 1 mole of CO2. Well, what does that mean? There's 1 carbon atom for every molecule of CO2. So thus there's a mole-to-mole ratio, and that's because Bob got his number. So this converts me to moles of carbon. And let's see, I think I have that number. It's 0.003376. I'm just going to keep a number of digits right now. I'm going to round later. Okay, that's for CO2, or carbon. Remember, this is moles of carbon. Let's do the same thing now for hydrogen, and you get there through H2O. So H2O, we start off at 0.0609 grams of H2O. Now change to moles of H2O, 18.02 grams per mole. And now there's 2 moles of hydrogen for every 1 mole of H2O. Why is that? Because there's 2 atoms of hydrogen for every 1 molecule of water. This, I think I calculated this. This was 0.00676. And remember, this is moles of hydrogen. Okay? So I'm going through my flow chart. Now I have to ask myself, at this point, is there oxygen? What do you think? Does the original unknown evil powdery white substance have oxygen? It doesn't say, right? In that case, we're not sure, so we're going to assume there is oxygen. If it doesn't say, you should assume there is oxygen. Okay? So we're going to go down the bottom half of this flow chart I made for you earlier. Now I'm going to go to mass of carbon and hydrogen. Okay? Same flow chart, same thing. Just kind of keep on going through it. All right. So, for carbon, The mass of carbon is what I'm working on now. Well, I've got 0.003376 moles of carbon. I can use a periodic table. 12.01 grams per mole of carbon. This will change me to grams of carbon. This turns out to be 0.0405 grams of carbon. Now I'm going to do the exact same thing for hydrogen. Mass of hydrogen now is what I'm going to work on. I had 0.00676 moles of hydrogen, and it's 1.008 grams per mole from the periodic table. And that'll get me pretty much the same number, 0.006814 grams of hydrogen. Okay? So now I've got the mass of hydrogen of each. Remove this out of my way. My next step, if you look at the flow chart, is to use that one formula to find the mass of oxygen. So the mass of oxygen will be the total mass minus the mass of hydrogen minus the mass of carbon. The total mass is given in the problem. It's 0.1014 grams. Mass of hydrogen, I just calculated it, 6814. And the mass of carbon, I just found that too, it's 4055. Let's see what this number is. It is 0.05404 grams of oxygen. Let's pause for a moment. If this number was 0 or very close to 0 as compared to the other numbers, what would that mean? It's not there. Okay, so if I got a number that was 0 or much, much smaller than all the other numbers, there's no oxygen. But I got a number, this is pretty comparable to the other numbers. There's oxygen for sure. Okay? Now, my next step, if you look at the flow chart, is to change to moles of oxygen. So, my moles of oxygen, how do I get that? Well, I take the number I just found, and I use molar mass from the periodic table, 16 grams per mole, and that turns out to be 0.00338, and that's moles of oxygen. Okay? Now let me go back, and I'm going to use the color blue here. Then, now I'm assuming these 3 atoms are in my molecule, and let me just put the subscripts X, Y, and Z in here. So there's carbon, there's hydrogen, there's oxygen. Okay, which variable is this number right here? Z, this is the moles of oxygen. If I rewind back a little bit here, the moles of hydrogen is right here, that's Y. This is the top of my page. And the moles of carbon is right here, that's X. So I know X, Y, and Z, or I know the subscript for each, because I have the moles of each. Remember, mole is the key unit. So I'm going to fill those numbers in. That's carbon, 0.003376. Hydrogen, where's hydrogen? Oh, there it is. 0.00676. And then oxygen, 0.00338. Okay, so I put in the moles for each one. I'm almost at the end. What will I do right now? I'm going to divide by the smallest, which is X, Y, or Z. Okay, yes, this is usually a tough part for students. What is the smallest number? X, Y, or Z? X, okay. We're rocking here. So divide all 3 by X. Y is the smallest number. Okay, what do you get? Gotta go to the next slide. You're gonna get C1H2O1. And that would be after rounding. You do have to round a little bit, but you're gonna round to the nearest whole number. Or CH2O. This is my empirical formula for the evil unknown substance. Now, I can also find the molecular formula because I'm given in the question, if you look back, 180 grams per mole of the original. So what I do is I take my empirical, I'll get a different pen color here, take the empirical, go down here, find the molar mass of the empirical formula. That, from the periodic table, that's going to end up being 30.03 grams per mole. And then now I'm going to find the molecular formula, or I'm going to find the difference through division. I'm going to take 180, the given of the molecular in the numerator, divided by the empirical in the denominator. And you math savants, what is this going to be? Number 6, okay? Approximately, you're going to round to the nearest whole number. And so you're going to take C1H2O1 and multiply the subscripts by 6, and you're going to get C6H12O6. This is the molecular formula. Okay? By the way, what's your best guess at this evil unknown substance? Sugar. Yeah, sugar. The one I just showed you earlier, I think. Or just, I showed you secrets. This is the one that we did review in class when we were doing that example. Okay, cool. So those freshmen can be released. All right.